Hi, this is Professor Stugard. This is our lesson on the dot product. So the dot product, which is also sometimes called the inner product or the scalar product, is found when we multiply the corresponding components of two vectors and then sum those results. What this means is that the dot product of two vectors is actually going to give us a scalar quantity. So again, the way we typically do it, if I have two vectors u and v, we're going to take the first components of each. So in this case, it's the a and the l, and we multiply those together. And then we do the same thing with each other component. So multiply the second components, in this case, the b and the m, and then the third components, the c and the n, and then we add all of those together. And we're going to get some scalar result. The dot product is going to tell us a lot of important information about the relationship between these two vectors, particularly when we combine about other information, specifically their magnitude, which we'll look at in just a bit. But one of the things I want you to also be very aware of is that this dot product notation is very, very useful anytime we want to sum products. So if there's some sort of mathematical operation where we're multiplying pieces in order and then summing those results, we can use the dot product to represent that mathematical idea in much more compact notion. And again, you're going to see that come up quite a bit, and particularly when we get to things involving calculus in chapter 14 and chapter 16 and chapter 15, where the dot product notation is going to be very useful so that we can write these very complicated ideas in a very short amount of space. So the properties of our dot products, well, the first property is that if I dot any vector with itself, so this first one, a dot a, it's going to result in the magnitude of a squared. All right. The second property is the commutative property, meaning that I can do it in either order. A dot b is going to equal b dot a. And that should make sense because, well, the dot product is just doing multiplication and addition. And I can do multiplication and addition in any order, which means that I can do the dot product in any order. Property 3 is our distributive property, which is very, very handy. Basically saying that if I have a dot b plus c, I can do a dot b, a dot c, and then sum those results. Property 4 is another distributive, where if I have a scalar, I can again distribute that scalar any way I would like, or factor it even. And again, that should make sense because, well, the dot product is just multiplication and addition. We know we can factor with those. And then our fifth property is that if I take the zero vector dotted with any other vector, my result is going to be 0. So we're going to start looking at some proofs now. And throughout our entire course, we're going to look at a bunch of different proofs and a bunch of different methods. But we're going to start with an easy one for this. So I want to prove property 1, that given some vector v with components a, b, and c, I want to show that if I dot that vector with itself, I'm going to end up with the magnitude of that vector squared. So typically, the way I want to do this type of proof or show this sort of result, I'm going to work on each side of my equation until I can show that each side is equal to one another. So typically what we would do here is, well, I'm going to start on the left-hand side and dot a vector with itself. And a lot of times we use kind of our shorthand notation, LHS for the left-hand side. And so when I dot something with itself, well, multiply the corresponding components. A times A plus B times B plus C times C. So, well, my result is A squared plus B squared plus C squared. Well, I don't think there's anything else I can really do on that left-hand side. So now let's take a look at the right-hand side. Well, to get to the right-hand side, which is the magnitude of V squared, first I'll have to calculate the magnitude. And, well, there's my formula right there. And then I need to square it. So now I'm working on my right-hand side, or RHS. And, well, what happens when I square a square root? Well, they're going to cancel out. So looks like the magnitude of v squared is a squared plus b squared plus c squared. Well, wait a minute. Now I showed that my left-hand side is equal to my right-hand side, and therefore the dot product of any vector dotted with itself is equal to the magnitude of that vector squared. And we just completed our proof. Now let's take a look at property 5 and do another proof. So given any vector v with components a, b, and c, and then the 0 vector, where the 0 vector has each component as 0, show that any vector dotted with 0 is, well, going to be the scalar 0. Well, this one's pretty straightforward. Take that left-hand side, and, well, when I dot it and match up my components, a times 0 is 0, b times 0 is 0, c times 0 is 0, and 0 plus 0 plus 0 is 0. And boom, that one was done. That was really, really easy. What I really wanted to stop and have you take a look at with this example, though, is that the 0 vector has my vector notation on top. All right? And we need that anytime we're doing a vector. Don't get lazy. If it's a vector, put that line over top. That's going to be very important so you don't make little tiny mistakes. You know, if you thought forgetting a negative sign was bad, well, don't forget your vector notation as well. And then obviously if there is no vector notation, right, my result is a scalar. There's obviously a difference between a vector and a scalar, and just make sure you're being diligent, you're showing discipline, and you're putting that notation correctly on each step as you do your homework, as you write your notes, and just as you work through any problems. Now let's talk about the dot product theorem. And spoiler alert, any theorem that has a specific name attached to it, in this case the dot product theorem, is incredibly important. And you're going to need this dot product theorem, and we're going to use this dot product theorem and exploit it quite frequently over the span of this entire course, and you're going to actually be using it quite frequently throughout any sort of degree studying physics or engineering. And so what the dot product theorem states is that if you have two non-zero vectors, a and b, and theta is that angle between them, that dot product a dot b is actually going to be equal to the product of the magnitude of each of those vectors, so the magnitude of a times the magnitude of b times cosine theta, which is a very interesting result given that, well, when I actually calculate the dot product of a and b, right, I'm just multiplying their components and summing them. Where does cosine show up? Well, let's take a look. And this proof is going to be a little bit different, where it's going to be a little bit more in depth. So if I start with vectors a and b, and I put those in standard position, I'm going to actually want to consider the vector a minus b as well. So hopefully you remember how we set up our triangle with a, b, and the vector a minus b. And we have that angle theta between them. And what I want to do to this triangle is apply my law of cosines, which is really the Pythagorean theorem, but with that little correcting factor, right? C squared equals a squared plus b squared. That's your Pythagorean theorem, except Pythagorean theorem only works for right triangles. So for non-right triangles, we had that correcting factor of minus 2ab cosine theta. Now, to apply the law of cosines relates the length of the sides of my triangle and the angle, one of the angles of that triangle. Now in this case, my triangle is created from vectors, which means the length of the sides of each of these triangles is going to be the magnitude of those vectors. So literally just plugging in the sides of my triangle into the law of cosines yields that expression. By the first property of dot products, though, if I take a look at that left-hand side, the magnitude of a minus b squared, well, I know that that's really that vector dotted with itself. Well, then if I apply property 3 to this expression, well, it actually expands exactly how we would expect it to expand. It's a very nice property of dot products. It's basically a binomial expansion. So I get a dot a minus 2 a dot b plus b dot b. Well, apply the first property again. We know that a dot a is really the magnitude of a squared. And we know that b dot b is really the magnitude of b squared. And so we had this when we plugged our sides of the triangle into the law of cosines. And now I want to substitute that result on my left-hand side. And there we go. We'll take a look now. What can we do now? Well, I'm seeing the magnitude of a squared and the magnitude of b squared on both sides. So let's subtract that from both sides. And so canceling those out on both sides, what I'm left with now is minus 2 a dot b equals minus 2 magnitude of a, magnitude of b cosine theta, and hopefully we see the last step is to just divide both sides by that minus 2, and voila, there's my dot product theorem. Given two non-zero vectors a and b with the angle theta between them, that dot product of a and b is going to be equal to the magnitude of a times the magnitude of b times cosine theta. As I mentioned, this theorem has its own name, which means it's incredibly important and it's very powerful, and it really lets us describe the relationship between two non-zero vectors with a single scalar quantity. Now, we also use algebra quite a bit to try to isolate cosine. And so if I just divide both sides by the magnitudes, I end up with this result as well, which is also incredibly important. In fact, both of these results are very important, and they're both used in, well, different ways. The nice part about this bottom value is that, again, we can take two vectors, and we know that if we take these two vectors, we apply the dot product and then divide by their magnitudes, that's always going to equal cosine of theta. And we know that cosine of theta is always bounded between -1 and +1, which means we actually have a nice bound, and I can actually describe the relationship between any two vectors with a single value that is bounded between -1 and 1, which is actually used in quite a few places. And you can Google cosine similarity and see how we use that, particularly in areas like data science, to compare vectors and how similar two things are. Let's talk about another definition, orthogonal. So if the angle between two vectors is pi/2, or 90 degrees, we call those vectors orthogonal. And so orthogonal and perpendicular are essentially synonyms in this case. And we're going to use the term orthogonal more often than we use the term perpendicular, because again, orthogonal has certain connotations, and we use it more frequently, again, when talking about vectors and in physics and things like that. So orthogonal and perpendicular are essentially the same things. We're just going to use the word orthogonal more and more frequently as we proceed through this course. Now, if two vectors are perpendicular and we apply the dot product theorem, what's going to happen? Well, a dot b is equal to the magnitude of a times the magnitude of b times cosine of that theta. But in this case, theta is pi/2. And what's cosine of pi/2? Well, it's 0. Now, if you didn't know that off the top of your head, well, you're definitely putting yourself at a disadvantage. Right triangle trig is going to be so crucial to understanding everything that comes in this course that you should absolutely spend way more time trying to memorize the unit circle and treat that unit circle as if it's your new times tables, right? You're now at a second stage of your academic career. The times tables were great when you were, doing algebra. Now your new times tables is the unit circle, and that is going to be what is critical, and being able to pull those values out just as quickly as you do with your times tables, which means practicing them as often as you had to practice your times tables, and it will make your life way, way easier. But if cosine of pi/2 is 0, because we are familiar with our unit circles, well, what's anything times 0? 0. That means the dot product is 0. And we end up with another theorem. Two vectors, a and b, are orthogonal if and only if their dot product is 0. So we showed it in one direction. We said that if they're orthogonal, if that angle between them is pi/2, the dot product has to be 0. However, this phrase, if and only if, means that it works in both directions. It means if they're orthogonal, we know it's 0. It also means that if it's 0, I know they're orthogonal. And you should really think about how you could try to prove that in the other direction. Our first example is, well, just asking the question, are two vectors going to be orthogonal? And all you need to do is calculate their dot product. So multiply their corresponding components. So 2 times 9, which is going to be 18. 6 times -3, which is negative 18. And what's 18 minus 18? It's 0. Therefore, the vectors must be orthogonal. Done. However, a much more common type of question would be to find the angle between two vectors in space. And so to find the angle between two vectors in space, we're going to use that dot product theorem, which means, well, we need to calculate the dot product. And so, again, I'm going kind of quickly through this. You should absolutely pause the video right now and stop, calculate the dot product between those two vectors, calculate the magnitude of each of those vectors, because we're going to need that information as well. And then once you've calculated both of those, then unpause the video and, well, let's make sure we get the same results. So I calculated the dot product is negative 3. Here are the magnitudes. The magnitude of u is the square root of 45. The magnitude of v is the square root of 35. Again, make sure you're taking the time to do this yourself. And now we just plug our results into that, well, dot product theorem, the one that we put a box around earlier. So the dot product was negative 3. We plug in our magnitudes. Now we just simplify following the order of operations. I get negative 0.07559 is equal to cosine theta, which means the last step to get theta by itself is to, well, use the inverse cosine or the arc cosine. And so if I take the arc cosine of that number, I'm either going to get 1.65 rads or radians, which is approximately 94.3 degrees. Now again, most of what we do in calculus has to be done in radians, but I understand, with things like engineering, we have a much better intuition for, well, the degrees. I have a much better intuition for what 94.3 degrees looks like than, well, 1.65 radians. So again, all the calculus is going to be done in radians, but it is a good idea to interpret your results so that it's useful, and, well, that's where degrees come in. So we talked about orthogonal vectors or perpendicular vectors. If two vectors are parallel, remember that means that the angle between them is either 0 or pi, either they're facing the same direction or opposite directions. That's what parallel means. If I apply the dot product theorem, well, what's cosine of 0 or cosine of pi? Well, it's 1. And 1 times anything is still that anything. So the dot product of two parallel vectors is going to be the magnitude of those vectors multiplied together. Next up is the scalar projection. So this is another one that's going to become very, very important, and we're going to use quite frequently. And again, if you've done any courses in physics, I'm sure you've done this already, but let's make sure we're on the same page. But the scalar projection, or sometimes called the component, of two vectors happens when we put those vectors in standard position, and we create a right triangle by drawing a line from the tip of B down to vector A so that it makes that right angle, as I drew in that picture. Then the length of the leg along vector A that is part of the triangle is called the scalar projection or the component. And so one of the reasons we call it the scalar projection, so projection is in shadow. So if you imagine the sun up here shining down, the shadow it casts is going to be our component. All right, so again, it's just that part of that right triangle. And again, we're going to call that the component of B along A. And obviously, order matters here. Now, we denote the component of B along A as, well, comp sub A and then B. Now, you can, if you want, put the vector notation over A. I find that that starts to get just a little bit crowded on my paper, and my handwriting isn't necessarily neat enough to, well, make that a good choice for me. I do know that I'm dealing with vectors because, well, B gets the vector notation. But again, it's kind of personal preference here. Now, we can actually solve for this component using right triangle trig. We're using SOHCAHTOA. Well, cosine is your adjacent, which would be the component, over the hypotenuse. And the hypotenuse, in this case of that right triangle, is the magnitude of B. And so cosine of theta must be the component over the magnitude of B. And, well, we can clear that fraction, multiply both sides by the magnitude of B, and solve for our component notation. So the component of B along A is going to be the magnitude of B times cosine theta, where cosine theta is that angle. And again, if you've done physics, you've probably done this a bunch of times with all of your different force diagrams, even if you didn't necessarily call it components or whatever. It's all just right triangle trig, which if I didn't mention it 5 minutes ago, I'll mention it again. Right triangle trig is crucial to being able to be successful in this course and, well, any other math course or engineering course from here on out. Now, what we can also do, and again, that definition is nice, but we can actually use our definition from the dot product theorem to simplify this a little bit. And so if I replace cosine theta with what I know cosine theta to be, based on that dot product theorem, here we go. And then, well, wait, the magnitude of B, and then I'm dividing by the magnitude of B. So I can actually cancel those out. And so we could write the component of B along A as the dot product of A and B divided by the magnitude of A. Now, besides the scalar projection, also called the component, we have the vector projection. Now, the vector projection is very similar to the scalar projection, but the vector projection is, well, obviously a vector, but the vector is going to have the same magnitude as the scalar projection, so they have the sizes are the same. It's just that the vector projection is now a vector that's going to be in that same direction as A. So again, notice the arrow now on my picture. We denote that projection. So again, the projection is a vector, the component is a scalar, but we basically do it the same way, just swapping out component for projection. So this would be the projection of B along A. Again, understanding how to do the right triangle trig is the most important part, and being able to derive it yourself. But we can play around with this a little bit as well. We know that the magnitude is equal to the component. So there's your component. And one of the tricks that we're going to be using quite frequently is if I know the component of something, and I want to describe that vector, and I know the direction, I need to use a unit direction vector. Now, we knew from our last lecture on vector basics that I can turn any vector into a unit vector, right, which preserves the direction but just makes it of a unit length by taking that vector and dividing it by its magnitude. And so we get our unit direction vector is now A divided by the magnitude of A. And again, if we want, we can simplify it a little bit because we have magnitude of A times the magnitude of A on the bottom, which is the magnitude of A, well, squared. And we could use the property one of dot products to write that as A dot A if you wanted. So it would be A dot B over A dot A. But again, that doesn't necessarily help us too much. And then obviously that vector A giving us direction and actually making it a vector. So we're talking about physics and engineering because, well, that's what most people use multivariable calculus for. And so one of the things we're going to look at quite a bit, and it's going to come up a lot, especially in later chapters, particularly chapter 16, is this concept of work. So work is a measure of the energy transfer that occurs when an object is moved over a distance by some sort of external force. So if you're moving an object from point A to point B, work is the energy transfer or the amount of energy that is necessary to actually have that done. Now, work is measured in the scalar unit joules or Newton meters, depending upon, I guess, who your physicist professor is. And in introductory physics courses, we're typically just define work as being force times distance, the amount of force times the distance. All right, but we're now at Calc 3. We can do better. Just like force is not necessarily mass times acceleration, it's mass times the change in velocity, work has got to be looked at again too, and we need to actually do a little bit better because force is not always going to be a constant. You're not always going to be able to apply a perfectly constant force to an object. And that distance, well, that distance is really going to be displacement now, how I get from point A to point B. Also, the force, well, that force is not necessarily always going to be applied in exactly the same direction as the displacement or the distance, which means that the force is going to be applied in a slightly different direction, or actually in any different direction than that direction that we're actually being displaced. What I need to calculate is actually the component of force along that distance. And so we know how to calculate the component of force, right? That's literally that definition we came up with our right triangle trig. So the component of force along that distance times the magnitude of the distance, which is, again, our displacement vector. But if I take this equation, well, we know how to calculate the component of the force along my distance. It's the, well, magnitude of force times cosine theta. That's my definition of the component. Well, if I rewrite this a little bit and put my magnitudes in front, so the magnitude of force times the magnitude of the distance times cosine theta. Wait a second, that should look really familiar because it's just the dot product. So it turns out work is going to be force dot distance or displacement, which means work really is force times distance, but it is a bit more complicated than just, well, saying work is force times distance. We're going to have to do a little bit more work and actually understand the physics behind it when we try to calculate calculate these quantities in the future. The last topic I want to talk about is going to be our direction angles in 3 space. So if I'm given a vector in standard position, meaning its tail's at the origin, and it's pointing out, and in this case my vector is v is given in pink, and we have vector v being ai plus bj plus ck, that vector v is going to make 3 separate angles which become our direction angles. So it's alpha with the x-axis, beta with the y-axis, and gamma with the z-axis. So our direction angles are going to be alpha, beta, and gamma. Now, the nice part is with our dot product theorem, those direction angles should be pretty easy to find. So we know by the dot product theorem that cosine of alpha is going to be v dot, well, if it's the angle that's made with the x-axis, and we know that I hat is, well, along my x-axis, it's my unit vector along the x-axis, then I can absolutely use that. So cosine of alpha is going to be v dot I hat divided by the magnitude of v and the magnitude of I hat. Well, calculate that dot product. V was the vector with components a, b, c. I hat, my standard basis vector, has a 1 for my x component and zeros. Well, if you do that dot product, that's just a. And also, we know that the magnitude of I, well, it's my unit vector. It's got to be just 1. So when I plug those results in, cosine of alpha is just a divided by the magnitude of v. It actually works out that this direction angle works out pretty simple. I could apply that same process and that same logic and find out that cosine of beta is b over the magnitude of v, and cosine of gamma is c over the magnitude of v. And now I can use that to find direction angles for any vector. So for example 3, let's say I have this vector I hat minus 2j hat minus k hat. And I want to find the direction angles. Well, the first thing I need to do is find the magnitude, because we know that that's going to be part of each one of my calculations. So find the magnitude of v. Again, pause the video. Did you find the magnitude of v? I hope so. It's the square root of 6. If you're skipping that step and not actually calculating this yourself, well, man, are you setting yourself up for quite a bit of failure, because the only way you get better at something is practicing it, and this is your practice. Now, once I know the magnitude of v, it's a pretty straightforward process to find all of my direction angles. So alpha is going to be a, and again, a is that component in front of I, which in this case, a is 1, it's 1i. So cosine of alpha is 1 over square root 6. Again, we're going to use the inverse cosine or the arc cosine. And so the inverse cosine of 1 over root 6 is going to be approximately 66 degrees. And we do the same thing, cosine beta. Again, my component in front of j is negative 2. Negative 2 over root 6, plug that into my inverse cosine. Beta should be approximately 145 degrees. And then lastly, for gamma, Cosine of gamma is -1 over root 6. Plug that into your inverse cosine, and there you go. We found each of our direction angles. Time for one last interesting fact about direction angles and one last example. So again, if I'm given vector v, which are my components a, b, and c, and we already know that cosine of alpha is a over the magnitude of v, and so on, well, I can actually solve fairly easily for a, b, and c. Just clear those fractions. If I multiply both sides by the magnitude of v, I get a equals magnitude of v cosine alpha, b is magnitude of v cosine beta, c is magnitude of v cosine gamma, and I should plug those back in. For my a, b, and c in my original vector, I now have my a, my b, and my c. Well, so that means I can describe my vector v using the magnitude and the cosine of each of my direction angles. But, well, notice each one of these components has that magnitude of v. And magnitude of v, right, any magnitude is a scalar. So I have the same scalar multiplied by each of these components, which means I can factor it. I can factor completely out of my vector. And then, well, now that I've factored out, I'm going to actually divide both sides by that magnitude. And the reason I divided both sides by that magnitude is that now if I look at this left-hand side, vector v divided by the magnitude of v, well, that's got to be a unit vector. That is a unit vector. That has to equal, that has to have a magnitude of 1. Well, we know how to calculate the magnitude. The magnitude is then going to be cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. Which leads us to our last example. Given vector v with direction angles alpha equal to 3 pi over 4, beta equals pi over 3, I can actually find gamma if I know, well, a little bit more about gamma. So in this case, we're going to bound gamma between 0 and pi over 2, which means quadrant 1. And I am actually going to be able to know and figure out what my last direction angle is based on my first two. So again, I'm going to take that expression that we just found, that the cosine squared of alpha plus cosine squared beta plus cosine squared gamma equals 1. And now we just, well, plug in alpha and beta. So cosine squared of 3 pi over 4 and cosine squared of pi over 3. Again, hopefully you know your right triangle trig. If not, take the time to pause it and figure it out. But cosine of 3 pi over 4 is root 2 over 2, and cosine of pi over 3 is 1/2. So you can plug those in. Now square those results. And root 2 over 2 squared is 2/4. 1/2 squared is 1/4. So I get 2/4 plus 1/4 plus cosine squared of gamma equals 1. Solve for cosine squared gamma. So cosine squared gamma must be 1/4. If cosine squared gamma equals 1/4, and again I'm trying to solve for gamma, we'll take the square root. So cosine gamma is plus or minus 1/2. And remember, anytime you take a square root when you're solving means you have to use the plus minus. This is one of the biggest mistakes that I see from Calc 3 students. They're so used to just taking square roots, and especially ones where it's kind of easy and it looks nice, and we know that the square root of 1/4 is 1/2. It's very easy to forget that to put that plus minus, but you have to put that plus minus. Now, cosine gamma equals either plus 1/2 or it equals minus 1/2. And because I know my right triangle trig, and I know in what quadrants cosine is positive, negative, that sort of stuff, I know that, well, in quadrant 1, it's got to be positive, which means gamma has got to be pi over 3. Again, take your time, work out all these problems, and if you have any questions, please email me. Good luck.